In this lesson, we're going to perform a hypothesis test for the difference between two means using the p-value method when we have independent samples. And we're going to start with an example. Scores on the National Assessment of Educational Progress mathematics test range from 0 to 500. In a recent year, the sample mean scores for students using a computer was 309, with a sample standard deviation of 29. For students not using a computer, the sample mean was 303 with a sample standard deviation of 32. Assume there were 60 students in the computer sample and 40 students in the sample that didn't use a computer. We can see that the sample mean scores differ by 6 points, 309 minus 303. The computer people did 6 points better than the people that didn't use a computer. Now we're interested in the difference between the population means. And what this is going to be, where it's sample, it's going to be a where they're giving you sample standard deviation. It's going to be a 2-sample t-test. Now, the question is it plausible that the difference between the population means could be 0? How strong is the evidence that the population mean scores are different? This is an example of a situation in which the data consists of 2 independent samples. 2 samples are independent if the observations in one sample do not influence the observations in the other. In the scores from the NAEP, the issue is whether the mean scores from both populations of students, those using computers and those without, are equal. And we're going to work on the null and alternate hypothesis. For the null hypothesis, in other words, does mu1 equal mu2? Therefore, the null hypothesis says that the population means are equal. Mu1 equals mu2. As an alternate to the null hypothesis, there are 3 possibilities. Mu1 could be less than mu2, mu1 could be greater than mu2, or mu1 could be not equal to mu2. Now, I'm going to show you another way to write this. This is what Minitab does, and we're going to get into Minitab in our last chapter. Minitab writes it like this. They say mu1, and they subtract the mu2. They show the difference. Minus mu2 equals 0. I'm doing simple algebra, and I'm just moving mu2 over. I'm going to do the same thing on this one. I'm going to say mu1 minus mu2 is less than 0. Mu1 minus mu2 is greater than 0, and mu1 minus mu2 does not equal 0. I like the way your book does it better, but I want you to be aware of what I've written in red because that is going to show up too. All right, now here's what we've got going on. We're using the following notation. We've got our population means, we've got our sample means, we've got our sample standard deviations, and our sample sizes just like in 10. The test statistic is based on the difference between the two means. And you take the x bar 1 minus x bar 2, and the mean of x bar 1 minus x bar 2 is going to be our point estimate. The method just described requires the following assumptions, and they're the same 3 from the confidence intervals. You need an SRS, both samples. The samples need to be independent. You're not taking a person and having them do a test twice. Okay, so they're independent, 2 different groups. And we need the normal condition. And you need that for both groups. I'm not going to write everything like I usually do, but we know what we're going to do in that instance. Now, here are the steps. I'm going to leave those there just in case you need them. We're going to actually do a problem. This is the same problem that we talked about at the beginning. It gives you all the data. And the question is, can you conclude that the population mean scores differ? Use the 0.05 significance level. So what I'm going to do, I'm going to test my conditions. And SRS both. The 2 groups are independent. And I didn't see anything about normal as I read it, but my groups are big enough to use CLT. All right, now here's what I'm going to do for my HO and my H1. It says, can you conclude that the population mean scores differ? So is mu1 different than mu2? And this is two-tailed. I'm going to just highlight it so I don't forget. And HO is going to be mu1 equals mu2. All right, and what I've got going on is I've got this part, I'm going to write in red. You don't have to write this. I've got my computer group and my no computer. And just like with the confidence intervals, I want to list my X bar 1, my S of 1, my N of 1, and ultimately I want to know what happens if I switch everyone to this. No computer is X bar 2, S of 2, N of 2, and mu of 2. And it says the sample mean scores for student using a computer was 309 with a sample standard deviation of 29. For students not using a computer, the sample mean was 303 with a sample standard deviation of 32. There were 60 students in the computer sample and 40 students in the non-computer sample. Now, based on my sample, I see that they are not equal. Okay, look at your sample means. 309 is not equal to 303. 309 minus 303 is 6. The computer people got a score at 6 more than the no computer people. Okay, so based on my sample. But we're going to see what happens when I do my test. So I'm going to go to inference. And I'm going to do a test. And I'm going to do, same thing, we don't do the proportions. I'm going to do 2 means. I'm going to do a t-test, not pooled. My null hypothesis, and you all can see that your calculator actually lists it like Minitab. So my null hypothesis is mu1 minus mu2 equals 0. My alternate hypothesis is mu1 does not equal mu2. So for us, it's going to be this. They've moved it over. I'm going to go back and rewrite these because of the computer, the calculator. It's mu1 minus mu2 equals 0. And mu1 minus mu2 does not equal 0. You can write those whichever way you want because our calculator is going to write them like this. Alex is going to write them like what I wrote in blue, and Minitab's going to write them like this. So either way is fine. I'm going to input statistics. My X bar 1 is 309. My S of 1 is 29. My sample size is 60. My X bar 2 is 303. My S of 2 is 32. And my N of 2 is 40. My significance level is 0.05. My test statistic, they're giving that to me there, is 0.953262. My p-value they're giving me, and I'm going to go to next. And that's going to be the graph. So I'm going to go back 1 to get my data. Then we'll come back to the graph. Here's what I'm going to write out. I'm going to write it up here just because of space for my conclusion. So here's what I did. I did a 2-sample t-test. And my test statistic is T. My T is 0.954. My p-value is 0.3434. Okay, so that is not a small p-value. All right, so this is what this is saying. If the p-value is low, HO is going to go. That p-value is not low, so HO is not going to go anywhere. All right, so what I'm going to say is I'm going to say, since our p-value of 0.3034 0.3434 is greater than alpha equals 0.05, we will fail to reject HO. All right, so HO is not going anywhere. All right, if HO doesn't go anywhere, we do not have enough evidence to conclude the true mean population scores differ. All right, and for my interpret the p-value, I'm going to say if HO is true, there is a 0.3434 chance of a test statistic as extreme or more extreme in either direction, or say both directions, in either direction, because it's two-tailed, and then give hours as t equals 0.954. All right, now we failed to reject HO. I'm going to look at my calculator, and you see that the p-value is much greater than the alpha value. It's way outside of that significance level, so I should have failed to reject HO. So I did the correct thing. And I want you to look at this one. And it's got TI-84 data. We're going to ignore that. But I want you to look at this Minitab output. Like I said, we're going to work on that in the next chapter. The difference is mu1 minus mu2. Okay, remember we talked about that, and that's what our calculator is actually doing. They're giving you the estimate for the difference. They're giving you a confidence interval. The main thing I want you to look at is the p-value, and they're giving you a test statistic. So that's what we will get when we look at Minitab. The output's going to look like that. It kind of looks like what we get on our calculator. I want you to look at this problem. We're not going to do this as a full test. I just want to do practice on the calculator with this. I've got a test was made of HO, mu1 equals mu2 versus H1. It's not equal, so it's two-tailed. Independent random samples were drawn from approximately normal populations. They give you the sample means, the sample standard deviations, the sample sizes. I want you to find the value of the test statistic and just decide whether to reject HO. We're not going to do this as a whole problem. We're just going to find T and decide whether or not to reject. So here's what I'm going to do. I'm going to go back to t-test. My null hypothesis is always going to be this, mu1 minus mu2 equals 0. My alternate is going to be they're not equal. Again, I'm going to go to next. I'm going to input my statistics. My X bar 1 is 73.9. My S of 1 is 4.2. My N of 1 is 23. My X bar 2 is 71.8. My S of 2 is 3.8. And my N of 2 is 17. And I'm at a 0.05 significance level. All right, my test statistic, and that's all I want you to write, is T is 1.652. And my p-value is 0.1072. That is a big p-value. We will fail to reject. 0.1072 is greater than 0.05. We will fail to reject. Looking at the calculator, I see how much further out the yellow goes than the dash. The p-value is much bigger than alpha. So we should fail to reject. We did the right thing. Our last one, and this is where they give you the data. So this will help you on the questions for 10 also if you are given data sets. It says treatment of wastewater is important to reduce the concentration of undesirable pollutants. One such substance is benzene, which is used as an industrial solvent. Two methods of water treatment are being compared. Treatment one is applied to 5 specimens of wastewater. Treatment 2 is applied to 7. The benzene concentrations in units of milligrams per liter for each specimen are as follows. And it says, how strong is the evidence that the mean concentration is less for treatment 2 than for treatment 1? We will test at the 0.05 significance level. All right, so and I'm going to do this as a full test. My conditions, I'm going to say SRS both. Now this one we need to, we're going to assume, and we know that we had independent samples. But we need to show the normal condition. So what you're going to do, you're going to type this in on your calculator. And we've not done one with 2 data sets, but watch. I'm going to type the first one into V1. And the second one, I'm going to go into V2. All right, I'm going to graph it. And I'm going to do my box plot. And if you look, it automatically pulls both of them up. All right, so it pulls up. There's my first one. There's my second one. They both look fine. I'm going to show both graphs on the same graph. And you want to make it look kind of like what's on your screen. My first one looks kind of like that, and my second one looks like this. And what I'm going to do, and like I told you, they're going to always be okay. I'm going to say no outliers, normal for both groups. All right, now what we're going to do, it says for my HO, it says how strong is the evidence that the mean concentration is less for treatment 2. So mu2, and look at how we're interested in mu2. So I'm going to start with my H1, and then I'm going to go back and get my HO. So here's my mu1, my H1. It says how strong is the evidence that the mean concentration is less for treatment 2. So mu2 is less than mu1. Now, this is what they're actually asking you. But the calculator is not going to take this because mu1 has got to be on the left. So what we're going to do is flip this. I'm going to go up here and write mu1. What I want you to look at with this next problem, I want you to look at the Minitab data. That's on the computer, and we will do that next week. This is Minitab data for that same problem that we just did. And I want you to look at the output. This would be your HO. This would be your H1. They put it like this, not equal to. Mostly what I want you to notice is your test statistic, 0.95. If you look up at the top, we gave 3 decimals, 0.954. And I want you to look most importantly at your p-value, 0.343. And like I said, it's the same thing that we got in the other problem. Read this problem, and we're not going to do a full test on this, but we're going to just practice this on the calculator. All right, so once you've read it, and pause the video if you need to, I'm going to go to inference. I'm going to do a test. I'm going to do 2 means, and I'm going to do a t-test. My null hypothesis is like it is. My alternate is two-tailed. So I go to not equal. I'm going to input my statistics. My X bar 1 is 73.9. My S of 1 is 4.2. My N of 1 is 23. And for the second one, I've got 71.8. I've got S of 2 is 3.8. And N of 2 is 17. And it's a 5% significance level. My answers, and notice that for the test statistic, they give you T equals 1.652. And for the p-value, I get 0.1072. If the p-value is low, HO is going to go. This is not a low p-value. 0.1072 is greater than 0.05. We will fail to reject HO. And like I said, we're not going to do a full problem. I want you to go to the next thing, and I want you to look at your calculator. And notice the p-value is not in that critical region. It's much bigger than alpha. We should have failed to reject HO, and that's what we did. All right, pause the video and read this problem. All right, and here's what we're going to do. It says, how strong is the evidence that the mean concentration is less for treatment 2 than for treatment 1? And we're going to start with our conditions. Now, this time I have a data set, and this will help you on that section 10.1 also. I'm going to go to statistics, and I want you to enter your treatment 1 in the first column, just like normal. And I'm going to go to the second column and enter treatment 2. All right, and when I do a graph of this, I want to graph both of them. These are 2 independent samples, so I need to graph them both. I'm going to do a box plot. And note that your calculator gives you both graphs. And we're going to put, for the conditions, we'll start this, and we'll put both graphs on the same graph when we do it. I'm going to say SRS both. I'm going to say independent. And for the normal condition, you're going to graph both graphs. So here's my first data set. And there's my second data set. And you want it to kind of look like your screen. Obviously, it doesn't have to look exact. And I'm going to say no outliers. Normal, check. Now, I want you to look at the what they want for H1. They say, how strong is the evidence that the mean concentration is less for treatment 2 than treatment 1? Okay, so this is what they want. mu2 is less than mu1. Now, the calculator will not take it like that. You have to have mu1 on the left. So I want you to do just like what you used to do in Algebra 1, and I want you to flip that. And I want you to say mu1 is greater than mu2. And if you think about it, it's the same thing, okay? If mu2 is less than mu1, mu1 is greater than mu2. So it's the same thing. So you always want mu1 on the left. I'm going to flip it. It will not affect our conclusion. We're going to conclude it just like what it says in the problem. All right, so here's what I'm going to do for my HO. I'm going to do my H1 first. It says mu1 is greater than mu2. My HO is going to be their equal. I'm going to write it again like the calculator does. Here's HO. Mu1 minus mu2, move that over, is 0. There's no difference. Mu1 minus mu2 is greater than 0. I move that over. And if mu1 is greater than mu2, when you subtract it, you're going to get an answer that's greater than 0. All right, the next thing we're going to do is go to the calculator to get this test statistic and get our p-value. All right, on the calculator, I'm going to go back out and I'm going to go to inference. I'm going to go the whole way out on inference. All right, and I'm going to do a test, and I'm going to do two means. I'm going to do a t-test. My null hypothesis is mu1 minus mu2 equals 0. My alternate is no, it's greater than 0. I'm going to input a data set. And when you look at this data set, the first data set, they're pulling in from that first column. That's exactly what we want. The second data set, I don't want to pull in from that first column. If you look at it right now, they're pulling in from V1. Hit EXE, hit enter. And then you want this to pull in from the second column. All right, so my second data is pulling in from the second column. I want 5% significant. And I go to my answer. And when I go to my answer, I'm going to go down here. It's going to give me my test statistic. And I'm going to do my screenshot up here because of space. All right, so here's what I did. I did a 2-sample t-test. My t is 1.590. My p-value is 0.0719. Okay, so if the p-value is low, HO is going to go. That's not a very low p-value. All right, so here's what I'm going to say. I'm going to say since our p-value of 0.0719 is greater than alpha equals 0.05, we will fail to reject HO. So HO didn't go anywhere. HO stays. We do not have enough evidence to conclude, and I would give it just like it was in the story. The true mean concentration is less for treatment two than for treatment one. All right, and my last part for my p-value, I'm going to say if HO is true, there is a 0.0719 chance of a test statistic as extreme or more extreme than ours, and ours was t equals 1.590. All right, and that's how we do a hypothesis test for the difference between two means with independent samples.